Hello everyone, my name is Kathan and today we'll be discussing the problem collecting numbers 2 from the sorting and searching problems of the CSES problem set. Let's begin. Let me read out the question for you. So this question is a direct extension from the previous question which is collecting numbers 1. So if you have not watched that video, I suggest that you do watch that video because I'll use a lot of ideas that I've discussed in the previous video. So I'll maybe link the previous video, that is the video for collecting numbers 1 in the I button above, right? So like I assume that you have watched that previous video and how did we approach that question. Fine. So let me read out the question here. You are given an array that contains each number between 1 to n exactly once. So we have elements from 1 to n exactly once. Our task is to collect the numbers from 1 to n in increasing order. Simple. And on each round, we just go from left to right, collect as many numbers as possible, right? And what we want to do output is actually in the previous question, you are given an array here which has elements between 1 to n exactly once, and you just tell me how many rounds will be there, right? So you want to collect numbers 1 to n in increasing order, and in one round what you do is you just go from left to right and collect numbers like 1 2 3 so on. If you are not able to collect some other number, you start a different round. So in the previous question you just had to print how many rounds you have to do to collect the numbers from 1 to n. But this question is a bit different. Here we are also defining some m operations. Now what are these operations? In an operation, you swap two numbers in the array. Okay. A task is to report the number of rounds after each operation. Right. Again. So what is an operation? An operation is simply swapping two numbers in the array. And after you swap two numbers in the array and you perform the same procedure of collecting numbers from 1 to n, how many rounds will happen? That's what you have to print. Right. So if you see the input here, this time along with n, you also have m. This n defines the elements 1 to n exactly once. So you will also have an input array which has elements from 1 to n. Fine. And then whatever this m is, the next m lines will describe the operation. What is an operation? It will just give you two integers a and b. These are basically the positions of elements which are needed to be swapped. So what you have to print is in this m lines, after you've applied that operation, after you applied that swap operation, what are number of rounds, right? So in the output you have to print m integers, number of rounds after each swap. So simple. You are initially given an array which contains elements from 1 to n exactly once, and there are some m operations defined. So what is an operation? Simply a swap operation. After the swap operation, what you have to do is you tell me how many rounds will be required to collect the numbers from 1 to n, right? And how do you collect the numbers? You just simply go from left to right, collecting the numbers in increasing order. Fine. So I guess the round concept I'll not go into detail here because we've already discussed it in the previous video. And constraints are pretty modest. Nm both are as high as 2 into 10 power 5, and ab, the positions of elements that are needed to be swapped, is between 1 and n. The example test case we can discuss when we discuss this question a bit more on iPad. But I guess that's about the question. Let's go on to the iPad and try to approach this question. First things first, let's talk about constraints here. So n being the number of elements in the array, and m the number of operations you had was somewhere in order of 10 power 5. So what does it say? You cannot do order of n into m solution because it's gonna cost you 10 power 5 into 10 power 5, which is 10 power 10 operations. So in 1 second you cannot do more than 10 power 8 operations. So like you cannot do n into m. So then if not 10 n into m, then what? Maybe you can do n plus m. So if you do n plus m, then it's gonna cost you what? 10 power 5 plus 10 power 5, which is somewhere in order of 10 power 5 only. But yeah, you can do n log m as well, right? You can also do m log n, so on. So basically with like either you can do something sort of a linear thing, or maybe you can append a logarithmic factor as well, or maybe add both of them, n log m plus m log n, right? And you cannot do n into m, or maybe n square into m square, so on and so forth, right? So these are the, you can say, the time complexities that we're looking for. Fine. Now what next? Let's take an example test case and try to understand this question a bit more. So let me take the same example. We had n equals to 5. So here there were what? 4, 2, 1, 5, 3. So these are the elements were given, and m was 3. So there will be 3 rounds. So there will be 3 operations, right? Not rounds, there will be 3 operations. What is an operation? Simply swapping 2 elements in the array. And after each operation, you have to tell me how many rounds will be required to collect the elements from 1 to n in increasing order, right? So what does a round constitute? You simply go from left to right, collecting elements in increasing order, right? Once you're not able to collect a guy, you start again, right? So we have to do that. So let's take the example here. First, so let me just write the indices here as well. So 1, 2, 3, 4, 5. Indices or positions. So I'm using 1 based indexing here. So n was 5, we had 5 elements, and we had to do 3 operations. And after each operation, you tell me how many rounds will be required to collect the numbers from 1 to n. So first operation was 2, 3. That is, you swap these two guys. So now the new array will look like 4, 1, 2, 5, 3. So how many rounds will be required, guys? First you start collecting numbers left to right in increasing order. So you'll collect 1, 2, and 3. So you'll collect 1, 2, 3 in the first round. Right, in the first round you'll collect these two guys. Then you'll collect 4, 5 in the next round. So there will be 2 rounds required. Fine. Now this operation performed. Now you remember the array is changed. Once this operation is performed, this is now your new array. Now we have to apply to operation on 1 and 5. So we swap the guys at 1 and 5. So you swap 4 and 3. So this 1, 2, 5 remains same, but then we have 3, 4. Right. So how many rounds will be required now? We have to collect numbers from 1 to n in increasing order while going left to right. If we cannot collect some number, we start again. So we start a new round. So we have 1, 2, yeah, okay. So these two will be in the first round, right? Because now after 1, 2, you cannot collect 3. So a new round will start. You'll collect 3, 4. So the second round, you'll collect 3, 4. Okay, but you cannot collect 5 now because 5 is before 4. And then in the last round, you'll collect 5. So there will be 3 rounds required here. Fine. Now 3 operations. So one more operation remaining, which is again 2, 3. So this operation was again 2, 3. It means swap these two guys. So now the array will look like 3, 2, 1, 5, 4. Now how many rounds required here? Let's see. First you collect 1, then you won't be able to collect any 1. So 1 round required here. 1 round. Then what you do? Then you collect 2. So second round for this. Okay. Then you collect 3, 4. So third round for this. And then one last round, fourth round for this. So here you have to output 4. So all in all, what you have to print is you have to print these things. So you have to first print 2, 3, and 4. So what does it mean? After the first operation, after swapping the guys 2 and 3, how many rounds will be required? Answer is 2. Then so once the array is changed, now you again apply the operation 1, 5. After you apply 1, 5 operation, this is a new array. In this array, how many rounds are required to collect the numbers from 1 to n? Which is 3. Now the array is changed. This is a new array. Now you apply the operation 2, 3. That is swap the elements at position 2 and 3. So now this is a new array. Now how many rounds are required in this array? 4. So that's how to print. So effectively you have to print 2, 3, and 4. M lines, M output. So I mean that's about the example test case. How do you approach this question then? Now one thing you can clearly see is like in the collecting numbers question, what we did is we exploited a fact that if x comes before x minus 1, then a new round will start. I'll come to this observation again, but we developed basically order of n log n solution. But like if we used a map to store the positions, but instead if you have just used a normal vector, then this log n factor would be gone, right? So then you could have come up with the order of n solution there. But here, like if you try to do that, you can say for all the m operations, you try to use the algorithm that we developed in the collecting numbers question. What will happen is for each of the m operations, you're going to consume order of n, or in the previous algorithm that we have developed, it was n log n, right? So you are going to consume this much time, right? Because what you're going to effectively do is for each operation, first you're going to swap the array guys and then run the algorithm that you developed, which was n log n. But it can be simplified to n order of n as well if we just use vector instead of a map. So order of n in the best case. But this still is a very high time complexity. It's an order of m into n. So you cannot definitely not do brute force. But it's a good starting point. Let's recollect our ideas. What was the observation that we made? The first observation that we made? The first observation was that the number of rounds will be at least 1, right? Like in the worst case, you just collect the elements 1, 2, 3, so on till n. But at least you'll have to do 1 round, right? So that was one observation. The second observation was if x comes before x minus 1, then a new round starts. right? In other words, if position of x was less than position of x minus 1, then new round will start, will increment the round. So in a way, like if you have these two observations, like you can calculate the rounds before we have performed any number of operations, right? So you can calculate, you can say this rounds before any operations is applied. Before any operations is applied, you can calculate this, right? So in actually order of n time, right? Order of n or order of n log n, doesn't really matter. You can calculate the number of rounds before any operations applied. Fine. So that's one observation is there. Now, but there's one more tricky thing here, right? We know we cannot do brute force. We cannot apply this logic after every swaps. Then what are you gonna do? You have to think some things matter, right? But this observation is still very crucial, right? In a way, what we want is after we apply the swap, we want to change something in these rounds, right? So what is this rounds? These are the number of rounds that will happen before any operation is applied, right? So whenever a swap happens, between the elements I and j, like elements at position I and j, maybe if in constant time you can change these rounds to some number, then the question can be solved, right? So I don't know like how are you gonna do it, but it gives you idea, right? We know we cannot apply brute force, but we do know how to calculate rounds, how many rounds we require before any operation is applied. Now after every operation is applied, what is an operation? Swapping two elements. If we can just figure out what is the change in these rounds in constant time, then our job is done, right? So maybe rounds are incremented or decremented from the initial, you can say the base number of rounds required, right? Then our job can be easy. Let's see how can we do that. Then we'll still use you can say the fundamental idea that we developed. If x comes before x minus 1, then rounds will have to increase, right? So use this observation. This observation is very crucial, right? So stick this thing in your head. And now let's try to see. Now let's simplify the constraint here a bit. So I'm saying that I'm gonna swap elements at position a, b, right? I'm calling it I, j, doesn't really matter. So we are gonna swap elements at position I and j. Can I just assume that I is always less than j? You can do that, right? So why if someone tells you to swap 3 2, it is same as swapping 2 3, right? So I'm just simplifying the constraint here that if I had given a task of swapping elements at position I and j, I'll always assume I is less than j. If it is not, I'm just gonna swap ij. So in a way, I will always be less than j. It doesn't change the question materialistically. Fine. So we have simplified the constraint. So if you have simplified the constraint, this is what will happen after like each operation. So now what we want to do is we have calculated the rounds before any operations is applied, okay? And after each operation, a swap happens between a position I and j. And now I know I is less than j. Why? Because if you just assume that, it doesn't change the question. Fine. Now, so if a swap happens between these two elements, let's try to see how the rounds can get affected, okay? And we will use our observation. If x comes before x minus 1, then rounds have to be incremented. Fine. So these two things are here, and these I think this will help us a lot. Now, you know one thing here that whichever the element is at position I goes ahead, right? So this guy moves ahead to j, and when swap happens, this j guy comes back to I. That you know. Now let's say you had element 4 here, right? If you had element 4 here, now 4 will go back few steps. Now look at this observation. Can you see how rounds will change if this 4 goes back? Like can rounds change when this 4 go back? As a matter of fact, let's say if you had 3 here, this 4 will move before 3, right? This 4 will move before 3. That is, you will have x before x minus 1. So the rounds will increase, right? So in this case, the rounds will increase. Let's take another example. If instead of this 3, there was, let's say, 5 here. So here you can see x was present before x minus 1. Now when 4 goes behind 5, this condition is no longer there. So you will you can say reduce the number of rounds, right? One less round will be required now. So if 5 is present, then a round will decrease, right? So what I'm saying is, guys, if we had 4 here, and you know this 4 is going back, right? So it's going back. And if in this portion, so in this portion is the portion where the position is greater than I and smaller than j, strictly, right? Strictly greater than I and strictly less than j. If you find 3 somewhere, it means when 4 comes here, you will have x before x minus 1. So the number of rounds has to increase by 1 from the initial rounds you had. Very straightforward, right? So r plus plus. But let's say if you had 5 here. If you had 5 here, it means initially you had x minus 1. X was before x minus 1. But since now 4 has gone before 5, the rounds have to decrease. You will have to consume one less round. I guess it makes sense. Let's take one more example here. Let's say, what do you think about value of I? Let's say this I was maybe the position I here was maybe the element 2. Okay. So we know that this guy from somewhere at the left goes towards the end. So this guy goes towards the end. Okay. Now hear me out. Let's say you had element 1 here. So if you had element 1 here, what do you have? You have x before x minus 1. But I know after the swap, this 2 is gonna move past 1. That is, this 1 exists in this portion. So what is this portion, guys? This portion is this portion, I, j, or maybe write it more concretely, the portion I plus 1, j minus 1. So in this portion of the area, right? So if 1 exists here, initially x was before x minus 1. But since 2 is gonna go past 1, one round will reduce, right? Because now you can collect 1 and 2 in the same round. So in this case, r minus minus. Makes sense. Similarly, let's say you had 3 here. If you had 3 here, initially you could collect 2, 3 in the same round. But if 2 goes past 3, because 3 is present in this portion, if 2 goes past 3, then x comes before x minus 1. Right? It means number of rounds will increase. Right? So what you have effectively seen here is if before the swap happened, these were the rounds you had, and let's call these elements that will need to be swapped as x and y here for brevity. Now depending on whether x plus 1 was present here, or x minus 1 was present here, or y plus 1 was present here, or y minus 1 was present here, what is this here? There is a portion where position is greater than I and less than j. We can change the rounds, right? So these were the rounds before the swap happened, and depending on whether these guys exist, that is x plus 1 or x minus 1 or y plus 1 or y minus 1, we can make changes to the round in just constant time. If you want, I can just show you all those conditions. I can write it here, but I'll just show you directly. It will just save me some time. So you can verify it for yourself that these are the same conditions, like which will change the round, right? So depending on whether x plus 1 or x minus 1 or y plus 1 or y minus 1 is found in the portion that is greater than I and less than j, you can increment the number of rounds. But is that all, or are we missing something? Think about it. Are we missing something here? So this is fine, right? So if these conditions happen, we'll definitely have to change the rounds like this. But there's one thing we are missing, right? What if you also had to, like, let's say ij, right? So we're talking about ij. What if the elements being swapped were consecutive numbers? So this conditions, if you observe, they don't consider consecutive numbers. They don't change the number of rounds if elements are consecutive, right? So if you had elements like this 1 and 2, and if you are swapping them, then what does happen here? See, now if 1 and 2 are present and you are swapping them, initially they were being collected in the same round, right? So 1 and 2 like this, since they are consecutive, right? So they will be collected in the same round. But if you perform a swap here, the rounds will increase, right? Instead, but if you had let something like 2, 1. So right now, these two are not collected in the same round, but after the swap, they will be collected in the same round. So the rounds will decrease again. These conditions are also very simple. I can just show you. So if x is equal to y plus 1, the rounds will decrease. So here you can say x is actually equal to y plus 1. So in this case, rounds will decrease. Why? Because these two were not able to be collected in the one round before, but now when you swap them, these two will be collected in the same round. That's why rounds have to be decreased, right? And similarly here, if x is equal to y minus 1, then rounds will increase. Why? Because these two were first collected in the same round, but after the swap, now we will have to take two different rounds. Fine. So if I have to combine all the conditions, I can just show you. So after a swap happens, you just have to check these conditions. That is, first these are for x plus 1, x minus 1, then y plus 1, y minus 1, and whether these numbers are consecutive or not. So maybe you can pause the video and verify these conditions are the same thing that we have discussed. And do we have to change anything else then? I guess we have covered all the possible points. Why? Because we only had to change something if x was coming before x minus 1. And by keeping this observation in mind, we have devised a perfectly valid conditions which change the rounds depending on the current operation that you do, right? And you can perform these conditions in any order, right? All that matters to us is if we have make sure that this observation is utilized well, we just update the rounds for current operation, right? Operation being swap. Now, if we have figured out this, then I guess we can write the pseudocode here, right? The pseudocode will be very simple. So I'll write a high-level pseudocode. First things first, we just find the number of rounds before any operation. I'll just call it rounds. Then I'll do all the operations, right? So for operations from 1 to m, right? So whenever I am entering this here, entering this loop, at every iteration, I'll have number of rounds calculated after the last operation, initially, before no operation is performed. Now, you take input I and j. This I know that I is less than j, right? So if it's not, I'm just going to swap them. Then we just update the rounds, right? So how do we update the rounds? Based on the conditions I just showed you, right? And these are all just constant time operations. After we updated the rounds, we can just print the rounds, right? And once you print the round, you actually apply the operation, right? So what is applying the operation? Swap the elements and change the positions, right? So apply the operation. And that's about it. So if you want to discuss the internals, we can discuss it during the coding part because it doesn't make sense here. But we can discuss the time complexity, right? But before that, if you have understood the explanation till now, please comment understood in the comment section of the video right now. And let's discuss time complexity here. So this we already know is going to consume order of n, right? Then we are running a order of m loop, right? So this is order of m loop. And in each iteration, this is a constant time operation. This updating is a constant time operation. Just doing some map checks, right? Or map or just normal vector checks. And we print it, then we apply the operation. Applying is also simple. We just swap the elements and change some positions. These all are constant time operations. So this is just an order of m loop. So order of c into m loop if you want to write it. But overall time complexity will turn out to be n plus m. So this is the overall time complexity. What is the overall space complexity here, guys? We just store the positions, nothing else. So the overall space complexity is simply order of n for all the positions. So that's about the pseudocode. I hope you have understood the question. Now let's move on to the coding part and wrap up this video. Alright, so here's the code. First we take n and m as input. N defines the number of elements in the array, or more precisely, we have elements from 1 to n exactly once. M defines how many operations we are going to perform. Then I'm taking the array input and storing the positions 1 based. I'm also storing the values because I'll have to use them for comparisons, but I'm storing the positions as 1 based. Now notice I've used unordered map here, but you can use a vector here as well. They both, when you try to actually, you can say, search for a given position, gonna consume constant time only. Why unordered map is not gonna yield order of n worst case time complexity is because we have unique keys from 1 to n. If we had too many duplicate keys, then it might give you in worst case order of n time, like for just seeing the whatever index this guy is. But since we know we have unique keys from 1 to n, this is just gonna give in just order of 1 time what is the position of a given element. So with that cleared out, there's one more thing you might be scratching your head. Why are we doing this? Why am I doing position of 0 equals to 0 and position of n plus 1 equals to plus 1? This is nothing more than a sanity check. Why? Because you will be accessing them here, right? So x plus 1, x minus 1, y, like you'll try to access these positions. That's why I'm just storing it like this. These elements don't exist in the array, but I have to define them, right? If you don't define them in C++, at least it will just create it. But this actually doesn't change anything here. Why? See, you're looking for x plus 1 or x minus 1 in range I plus 1 to j minus 1, right? And you know for the fact that the 0 and n plus 1 is never gonna be in this range I plus 1 and j minus 1. Why? Because I and j are in range 1 to n, right? So in the worst case also, you will be looking in a space from second guy till the second last guy. So any which way, these positions are not gonna create any problem, right? So like these conditions will never get satisfied because those positions cannot exist between I and j. That's one thing. So once that is cleared out, let's first count the number of rounds without any operation. So this just consumes order of n here, right? If x is before x minus 1, we just increment the rounds. This time this is just a constant time operation, so this is just order of n loop. Then for each operation, we first take the position that we have to swap. Then again, if I is greater than j, I'm gonna swap ij because I am assuming that I is always less than j. Then I take out the elements x and y, and then these conditions, right? So depending on whether x plus 1, x minus 1, or y plus 1 or y minus 1 is present in that portion, that is positions I plus 1 to j minus 1, right? So if they are in this portion, we increment or decrement the rounds. And also we have to handle the case when we have consecutive elements. And then once we have handled all the cases, we can print the number of rounds and then perform the operation. Simple. Performing the operation is simply swapping and just updating the positions in a map, right? And what is the total time complexity, guys? So the time complexity here, it was consumed order of n. Right? So these all is just input. That is fine. If you want to count this, it will be order of n here as well, right? Because this position map that you have. So order of n here, order of n here. Then for this entire loop, there is only a constant time. These are all constant time operations, right? So order of n plus order of m. Space complexity, just order of n for storing all the indices. So yeah, I mean, that's about the code. I hope you liked the video, you learned something out of it. And if you did, please give it a thumbs up, and I'll see you in the next one.